Hi and good day everyone. We are from Group 1. I'm Loija. Today we will present our findings on the suitability of SAGO starch for international food applications, identify core quality bottlenecks, and outline a strategic roadmap for successfully entering the highly demanding Japanese market. Before penetrating international borders, we must recognize that the Japanese food industry exhibits a high demand for clean label thickness, noodles, and confectionery.
SAGO starch possesses unique physical, chemical, and functional properties that influence its performance in food application. It contains 24 to 31% aminos and exhibits C-type crystalline structure. The starch granules are generally round or oval with a smooth surfaces and an average size of 30 to 40 micrometers. Functionally, SAGO starch has a high swelling power and rapidly gelatinizes when heated, producing high viscosity and excellent thickening properties. Due to its relatively high aminos content, it forms strong and rigid gels. However, it also has a strong tendency to retrograde during cooling, which may lead to opacity and water separation. This characteristic makes SAGO suitable for various food products while highlighting the importance of proper processing and storage conditions. Industrial SAGO starch production uses a fully mechanized wet milling process to maximize starch recovery and ensure product quality. The process begins with harvesting mature sago palms and transporting the logs through river waterways to preserve starch quality. The logs are then debarked and cut into smaller sections before undergoing dry rasping and pulping to release starch granules from the pits. Next, the starch slurry passes through centrifugal sieving to remove fibrous waste, followed by hydrocyclone refining to eliminate impurities such as sand, proteins, and residual fibers. The purified starch milk is then dewatered and dried using a pneumatic flash dryer until the moisture content reaches approximately 10 to 12%. Finally, the starch is sieve graded and packed for commercial distribution. Proper control of purification, moisture reduction, and packaging is essential to produce high-quality sago starch that meets international export standards.
Hi everyone, I'm Anna. A primary issue in locally scored cycle is the color degradation. If the harvest log is set too long before recipe, endogenous polyphenol oxidase reacts with air, kissing in enzymatic browning. This reduces the Venice index, a massive red flag for Japanese buyers who demand absolute purity.
Second, our evaluation reveals severe viscosity instability. On a rapid viscoanalyzer profile, the starch displays a blunted peak viscosity and excessive breakdown during holding phases. Biochemically, this is caused by processing delays at the local mill, which trigger endogenous alpha amylase to cleave the starch alpha 1,4-glucosidic bonds, reducing long polymers to short chain dextrins. Furthermore, utilizing untreated recycled processed water fosters microbial fermentation, exposing the granules to exogenous enzymes and organic acids. For our target applications in Japan, such as noodles and confectionery, this structural volatility is catastrophic. It causes noodles to lose tensile strength and dissolve during boiling, while causing confectionery gels to weep water via syneresis. This directly ties into our second bottleneck, Japan's stringent regulatory landscape. Japan operates a strict positive list system for chemical residues. Local mills frequently apply excessive sulfur dioxide or bleaching agents to fix the starch whiteness index. However, if these residues exceed Japan's default enforcement threshold of 0.01 parts per million, the shipment faces immediate rejection at the port. Microbiologically, Japan enforces a rigid limit of less than or equal to 1,000 spores per gram for spore-forming bacteria in starch matrices. Due to open settling pits at the local supplier, the baseline biological load exceeds this safety cap. Finally, a complete lack of digital batch traceability from the sago farms to the container fails Japan's mandatory HACCP import protocols.
This slide focuses on process optimization. The first improvement is using an optimized grading machine. It can help extract more starch from the sago beach and reduce material loss during processing. The second improvement is upgrading to a hydrocyclone purification system. It can remove fibers and other impurities more effectively and helps produce high purity starch. The third improvement is adding food-grade ascorbic acid during the rasping stage. It can help reduce browning and keeps the starch whiter. Finally, automatic monitor system can be used to control the production process more closely. It can help reduce contamination risk and ensure consistent quality cycle in every batch.
Another critical aspect of quality assurance is water management and sanitation. During SAGO starch extraction, large amounts of water are used and often recycled. If this water is not properly treated, microorganisms and starch-triggering enzymes can accumulate. These contaminants may break down starch molecules, causing viscosity instability and inconsistent product performance. To address this issue, we recommend a closed-loop water treatment system. First, mechanical filtration removes suspended solid and organic impurities. Next, UV sterilization reduces microbial contamination without leaving a chemical residue. This ensures that recycled water remains clean and safe for reuse throughout the extraction process. By controlling microbial growth and maintaining water quality, the starch retains its desired viscosity and functional properties. As a result, the final product becomes more consistent, safer, and better suited to meet the strict quality requirements of international market.
International standard completion is important for exporting SAGO starch to Japan. First, HACCP should be in practice throughout the production process to identify and control possible food safety and hazard. It helps reduce contamination risk and improve product safety. Second, ISO 22000 can enhance food safety management and help maintain consistent product quality. In addition, SAGO starch should comply with Japanese agriculture standard. It helps ensure products meet JAS quality and safety. Finally, a digital traceability system can be used to check each batch of SAGO starch from raw material source to export. It provides better transparencies and increase consumer confidence.
Hi everyone, I'm Anan. Although our analysis show that the currency raw SAGO starch poses significant quality and regulatory risks, these bottlenecks can be fully addressed through targeted food engineering interventions. By immediately doing at the rasping stage to perceive the wetness index, upgrading a UV-treated closed water loop to stabilize the viscosity, and mandating HACCP certification to establish starch batch traceability. We can systematically bridge this quality gap. This can transfer the product from a local commodity into a highly competitive product that can be exported to Japan.